How many people used graphing for the first one? Like on your calculator, do graphing? Okay. Yeah. How many people did elimination? Anybody do elimination? Yeah. And then substitution, which I figured would be most of y'all. Okay. What made you do substitution? They were both equal to y, so you can make them both equal to each other. Both being equal to y also helps with graphing, right? You can just type them in the way that they are. Good. Did anybody not get these? You need to see it. All right, and you did elimination? You did attempted elimination? So, substitution, made them equal to each other. All right, so when you make them equal to each other, we're going to have x squared minus 5 equals negative 3x plus 5. Because it's a quadratic, you want everything on the same side as the variable being squared. So I'm going to add add 3x over, and then you're going to subtract 5 from the negative 5 already there, which would give you a negative 10. So now you have the quadratic x squared plus 3x minus 10. Here you would basic factor. So you would think what multiplies to give me negative 10, that adds to give me a positive 3. That would be positive 5 and negative 2. So we have an x value of negative 5 and an x value of positive 2. To get their matching pair, you would plug it into one of the original problems. It doesn't matter. I actually did x squared minus 5 on my paper. Negative 5 squared is 25. 25 minus 5 is 20. So that's where negative 520 comes from. And then plug in the 2. 2 squared is 4. 4 minus 5 is negative 1. So that's where this one comes from. So what type of functions were these? Your first one is what? It was linear. It was a line going down, right? A negative line. And then the other one was a positive quadratic, so it was going up. So if you graphed it, you probably got something like this on your calculator to show where it crosses twice. All right, part B. How many people, let me tell you the answer. You should get negative 1, negative 7. And only negative 1, negative 7. Which means what's happening with these two quadratics? They're only crossing once, specifically where? At the vertex. Well, that's not true. Oh, wait, is it?
No.
I didn't see it. Hold on, I'm just guessing. But they're both positive. It should only be one time, though. I did elimination personally with this one. Did someone do something differently? Did you do substitution again? Did you graph it?
I graphed it.
You graphed it again? Okay. How do we want to see it? Because I see lots of confused faces. So do you want to see elimination or substitution? You want to see elimination? Okay, so what I did with elimination is I multiplied my second equation by a negative 1. Okay. Before you do that, though, you do have to make sure each piece is represented. So my top equation is still y equals 3x squared plus 2x minus 8. My bottom equation is 2x squared. I put in a 0x and then minus 9. I left the top alone. I multiplied the entire second equation by a negative 1. So this gives me negative y, negative 2x, negative 0x, which doesn't matter, and then a positive 9 on the end. Y minus y eliminates, leaving me a 0 in its spot. 3 minus 2 is x squared. 2x minus 0 is a 2x. Negative 8 plus 9 gives me a positive 1. But this quadratic multiplies to give you 1, adds to give you a 2. That's going to be x plus 1 and x plus 1. So we get an x value of negative 1. It's just one x value because they're both the same thing. right? So you only get x of negative 1. And then choose which one you want to plug it into. I did the second one. 2 times negative 1 squared is still just 2. And then 2 minus 9 gave me negative 7. All right. So a little review from last week. We're doing our last section of chapter 3 today, which is a system of inequalities. Okay, so we did a system of equations last week, and then we did quadratic inequalities on Thursday. So now we're going to put those two together. We're going to do a system of inequalities. Okay. So in a system of inequalities is a set of 2 or more inequalities in the same variables. Okay, an example is shown where I have y is greater than or equal to x squared minus 1, and then y is less than x plus 1. Okay. A solution of a system of inequalities in 2 variables is an ordered pair that is a solution to each inequality of the system. So you can plug it into both of them and then make both statements true. Okay. And a graph, the graph of a system of inequalities is the graph of all the solutions of the system. Okay. If I know you don't have color on your side, look up here. So when you graph each individual inequality, colors are good to do. When we do shade today, make sure it's light. And then where the shades cross over, you'll make darker because that's the solution area. Okay, anything in that shaded region is going to be a solution to the whole system. All right, so that this graph matches with the inequality that I gave you. So there's the parabola, it's solid. We shaded above the vertex. My line is dotted. We shaded, it should definitely be below. Or I can just change the sign. Oopsie, that should be greater than, shouldn't it? To make it match that graph. Oh, it's even wrong right here too. Y is greater than x plus 1. It's above it.
Yeah, but no shaded part is below it. Like it's below the line.
What's that? The blue is above. Oh, I see. Okay, book. I see. So the book should not have this part. There we go. We should have this part. Okay, we got this figured out. There we go. So it should be all of this, and then where they cross over each other, thank you, is this section right here. So above the parabola and under the line, our solution region is going to be that little piece in the corner. Call the book people. There we go. All right, so we're going to do it. Our first two, we're going to do it with just lines. That's something you do in Algebra 1. With the system of inequalities, you do it with 2 lines. So we'll start there first, and then on the back, we'll start throwing in some parabolas. And of course, we got to do a nice little real life problem. Okay, so let's remember how to graph lines. Here we go. We have y is less than or equal to negative x plus 1. So where am I going to start this line? Positive 1 where? On the x or the y? On the y. All right, and then how is my slope going to go? Down and over 1. Good. I can go backwards as well. Will these be connected with a solid or dotted line? Solid. How do you know that? It's equal to. Good. And now are we going to shade above or below? I heard it. below. Good. So this one is solid, and we're going to shade below. I'm going to do a little. So we're going to go under the y-intercept, so down here somewhere. Remember to shade light. Because you want to see where the shades cross over each other. All right, my next one is y is greater than or equal to x plus 3. Where does this line start? Positive 3 on the y-axis, and then my slope is going to go up and over 1 or down and back 1. Is that going to be a dotted or solid line? This one's going to be dotted or dashed, both mean the same thing. All right, and are we going to shade above or below the line? We're going to go above the line. All right. So, where do my shades cross over each other? See in this little quadrant right here? So that is our solution region. Okay. Now, if I asked you, is the point -4, 2 a solution to this system, would you tell me yes or no? Okay, how come? It's in the shaded region. -4, 2 is right here. You could also plug it into the equations, and it would make them both true. Okay, how about the point -2, 3? -2, 3, right here. Yes. What about the point -2, 1? No. Why not? What's the difference between those two? Dotted line versus a solid line. Okay, remember solid means equals to, dotted means not. Okay, so if it's on a line and it's solid and it's on the outline of the region, then you're good to go. How about the origin? No. It's not in both shades. What's definitely not a solution?
2, 2.
2, 2 is definitely not one. What'd you say? 4 what?
Oh, I said 4.
4, 2, definitely not a solution. They're a nothing. All right, so watch out for that. Yep, I can't graph that, sorry. But you're correct. All right, my next one. Here we go. Y is greater than or equal to -3x plus 1. Where is this line going to start? Where y is a positive 1. How am I going to move from here? Here you go. 1, 2, 3 over 1. 1, 2, 3 over 1. I can also go backwards. 1, 2, 3 back. Will this be solid or dotted? It will be solid. Am I going to shade above or below? Above. We know that because we're greater than. So solid line. I have both eyes and I still suck at drawing lines. And we're going to go above it. So again, my shortcut is I found my y-intercept and I went above. So I know I'm in this section right here. All right, our next one is x plus y is less than 1. It's different. It's in standard form now, not y-intercept form. So what should we do? Subtract that x. So we have y. Now we have -x plus 1. Is that going to flip my sign, subtracting the x over? No. It only flips if we multiply or divide by the -1. All right, where is this line going to start? Also a positive 1. How's it going to move? Down and over 1. How are we going to connect these points together? With a dotted line. Good. And are we going to shade above or below? Below this time. There we go. And below, so find my y-intercept and go down. So we're underneath the line. So can we see where they cross over each other? It's like this little wedge right here. So again, if you're doing just pencil, okay, I can kind of show you on my notes up here. I did it in just pencil. Do just like the straight lines, and then shade in darker where they cross over each other. Okay, if you don't have a colored utensil. If you got colors, please use them. If you don't have colors, there's still a way you can show me like where they're crossing over each other. Okay. What is a solution to this system of inequalities?
2 -2.
2 -2? Do y'all agree? Yeah, because in the yellow, what is a solution? 0, 1 is not.
It's a solution because it's on the solid line.
0, 1?
Yeah.
Oh, I definitely went to the X. I went to the X. Yep, you good. That's the y-intercept. We're good. I was thinking 1, 0. 1, 0 is not. Sorry. 1, 0 is on a dotted line. 0, 1 is the y-intercept. That is good. Because part of it is on a solid line, then it's okay. It's included. Yep. How about 4, 0 over here? No? How about 0, -4 down here? No.
0, 1 isn't a solution because it doesn't. It's on the solid line and a dotted line.
But the solid line makes it okay.
But if you put in the X plus 1 is less than 1, it's 1 is less than 1, which is not true. So it doesn't satisfy.
I see. There you go. Plug it into the equation. It has to work for both. Thank you, Brennan. It has to work for both. Y'all see what he was saying? We got a case of the Mondays over here. Sorry. So if we use 0, 1, so the second equation, 0 plus 1. So because it's not equal to, it doesn't satisfy both. So that's why. So that's why that point would not be a solution to the whole system. It's only a solution to the top one, not the second one. It is close. You're right. Thank you, Brennan, for helping me out. It needs to be a double solid. Yep. Thank you, sir. There we go. Math teachers are here too. Okay. Ready for parabolas? Yeah, I should follow my own advice is what I should do. I said graph and equations, right? Here we go. On the back, we now are throwing in some parabolas. So my first one is a parabola and a line. Okay. So don't forget speed graphing. It's here to help us. Our first one, y is greater than negative x squared plus 4. Can make this one red. All right, where is this parabola going to start? At positive 4. This is also its vertex because we're missing that middle piece. So this is also going to be the vertex of this parabola. Okay. Speed graphing. Remember that's the 1, 3, 5, 7. Am I going to do that going up or down from this vertex? Going down. Again, you do still have graphing calculators. You are welcome to type these in, go to your table, and plot in points. And then down 5. Like that, if you're ever not sure. Is this parabola going to be dashed or solid? It's going to be dashed. And are we going to go above or below the vertex? We're going to go above the vertex because it says y is greater than the parabola. So we're going to go above. So that means all of this area out here. It's like a sunshine.
Also, for a parabola, you go all the way around.
Correct. Yep. All the way around. Our next function is what type of function? Linear, so it's going to be a line. So where do we start my line? Positive 2. From here, how am I going to move? What about 1? Okay. up and over. How am I going to connect these points? Dotted or dashed line. Good. And according to our symbol, are we going to shade above or below the y-intercept? Above. So y-intercept, we're greater than, so we're going to go up. Like this. So my shaded region, my solution area, is going to be everything outside of my parabola and above my line. So it's not going to include that little piece in between, because that little piece in between is just blue. We see that? That was just my line. This is when colors kind of help. It's everything above the parabola and above the line. So it's that top corner, not including where they intersect each other. All right, someone give me a solution to this system. -4, 2. Absolutely. It is definitely in my region. Someone give me not a solution. 0, 0. -2. Is it -2, 0 or 0, -2? 0, -2. Correct. That is not going to be part of it. Exactly. Either one would have worked. That's not a solution either. Give me a solution that is.
0, 565.
That I can plot on the graph and show you. -5, -5. What'd you say with the 4s? -4, 3. Good. Good. Could you use the point 0, 4? No, why not? It's on a dotted line. Good. All right. Here we go. One more with me before we get to our real life modeling. All right, y is less than -x² plus 3. So where is this parabola going to start? +3. That is my vertex, right? So we're missing the middle piece. Can we speed graph? Yes, are we going to speed graph up or speed graph down? Speed graph down. Down 1 over 1. Down 3 over 1. Down 5, which goes off my grid. It'd be like down here. Boop. Are they going to be connected by a solid or dotted parabola? Dotted. And are we going to shade above or below that parabola? Below. So find your vertex, go down. So it's going to be everything inside. Oh, I'm going to do it this way. Next parabola. Where's it going to start? Is -3 my vertex? No, this time it is the y-intercept and only the y-intercept. Okay, so digging back to what we did Thursday. To get my vertex, we're going to have to do opposite b over 2a. Okay, that happens sometimes. So opposite b over 2a for this second parabola will be -2 divided by 2 times 1. So we have the x part of my vertex is -1. How do we get the other part of my vertex? Plug it in. So y equals -1 squared plus 2 times -1 minus 3. -1 squared is 1. That's -2 minus 3. What do you get? Hold on, I feel like I messed up. Yeah, it should be y equals 0. What did I do wrong? Opposite b over 2a. -2 over 2 is -1. -1 squared is 1. So -1, -4 is down here. It's all good. All right, so my speed graphing has already started for us. We're going to keep going. So we're going to go up and over 1. Then we can go by 3. 1, 2, 3. 3, and then 5, like that. Will this be connected with a solid or dotted line? Solid parabola, excuse me, not a line. There we go. Are we going to shade above or below this parabola? Above. Find your vertex. Go above it. So do we see the region in which they intersect each other? Yeah, this little piece in between. What is a solution?
0, 0.
0, 0. Woohoo! The origin works. What is not?
0, 4.
5, 5 would not work. 0, 4 would not work. Good. -5, -5 would not work. -5, 5 would not work. Any of my corners. Yeah, there we go. Let's get them all on there. None of my corners would work. Good.
-4. 0, -4.
Nope. None of my 4s would work, would they? Would any of my 2s work?
-4.
0, -2 would work. It's barely in, but it is. -4, -1 would not work. What?
It's on a solid line and it's in the area.
-4, -1?
Yeah. -1, -4, whatever.
-1, -4 right here. Yes, that one would be okay. Yep. It's on the boundary, and the boundary is a solid line. And you could always double check by plugging it in to the equations. All right, what's up?
0, 2.
0, 2. Yep,
Yeah.
that would work.
4, -1.
4, -1 would not. That would be no. Yep. Oh, I see what you're doing. Okay. All right. Let's talk about tuna cans.
No.
All right. A tuna cannery is designing a new cylindrical can. The height in millimeters and the radius, also in millimeters, are related by the inequality h is greater than or equal to 1/40 r squared. The cannery has the following additional constraints. The height must be no more than 30 millimeters greater than the radius, and the area of the base must be at least 1,600 pi square millimeters. Write and graph a system that represents the situation, and find one possible set of dimensions the cannery can use. All right, well, how could we... So we have one, right? Here's one inequality, and they've given me 2 more. Okay. The next one, the height must be no more than 30 millimeters greater than the radius. So how could I put that as an inequality?
H is less than or equal to R, and I was just saying, no, man. H plus,
So h, my height, must be no more. So it must be less than or equal to, good, 30 millimeters greater than the radius. R plus 30. Yep. So there's our second inequality. Then there's a third one. Yeah, the area. The area of the base.
the radius needs to be at least.
So area must be at least. So it must be what? Greater than or equal to 1,600 pi. All right, let's dig deep. What's the area of a cylinder? There you go.
That makes that simple.
or the circle, the top of the circle. Yeah. So we're going to say pi. Come on, pen. There we go. R squared. Pi's cancel. So we have r squared is greater than or equal to 1600. We can square root both sides. We have 40. We also have negative 40. But we're not going to have a negative measurement. Good. So our radius must be greater than or equal to 40. So there's my third one. So we have 3 pieces that we're going to graph.
How do we got that third one?
Okay? So in the terms of R's and H's, R's are your X's, H's are your Y's. Okay? And I was nice and I kind of gave you, plotted and labeled your graph for you already. So R must be greater than or equal to 40. That's going to be a solid line going straight up right here. It's not a function. And greater than means we are over here. So the measurement of our radius has to be 40 millimeters or more. You want to do the green one next, the line? All right. Yeah, I agree. So that one's going to start at 30. Okay. My R is just an R, so we can go up 1 over 1. Now notice my scale, they're the same, right? So up 1 block over 1 block is going up 10 over 10, so I'm allowed to do that. Does that make sense? So always double check your scaling. So up 10 over 10 simplifies to 1, so we can continue this way. Solid or dotted? Solid. Straight above or below? Below this time. Okay, so we're starting to see something. Something's happening in that bottom right corner. I know, right? It's the most fun. Calculators are a great thing. I would definitely, what I did, I'll even show you on my paper. I made a table and I looked at the values on my calculator and there's 4 of them that are very nice that we can graph. I'm going to show you. All right, so I'm going to put this into my y equals. But clear this out. Don't need this. Don't need this. All right, we're actually using red, so we'll do that. So 1 divided by 40, I'm going to put that in parentheses. And then I'm going to do x squared. Okay, I'm going to go straight to my table. Okay, straight to my table. All right, well, we know it starts at 0, 0, right? That's a point I can plot pretty easy. So we know 0, 0. Now we're going by tens, right? We're going by tens. Instead of scrolling, do you want to see how to make your table count by tens? Would you like to see that? Above window, it says table set in blue. So second table set. So where does it start? And then the next one is what are you going to count by? So I'm going to change that to a 10. So my table will jump by tens. Right, I'll have to scroll through all of them. Right, because my table goes what, to 100? That's a lot. I mean, my graph on my paper. So go back to your table. Now my x's are counting by tens. Okay, so 10 and 2.5, not the easiest one to graph. Could I plot 20, 10 pretty easily? Yep, I like that one. Whoop, 20, come on. There we go. So 20, 10, about right here. My next one that I like is 40, 40. 40, 40. What was it? 60, 90? Okay. I think, yeah, nothing else could fit. Solid or dotted? Solid. And above or below? Above. So we're on top of it. All right, so where do all three of these overlap each other? Yeah, this little piece here in the middle. It's just that little piece. Yep. That's under the green. It's to the right of the blue, and it's above the red. Is that little piece in the middle. Now, the question was, find one possible set of dimensions that the cannery can use. Okay, well, give me a possible dimension that it could use. 40, 50 would be okay. What else? 50, 70. Yeah, there you go. That's right in the middle right here. 40, 40 would be okay. These are all correct answers. Take your pick. 60, 40 would not work. It's out here.
I mean, I'm sorry, wait.
40, 60? Yes, that would work. My paper, I used 50, 70 because it was inside. So if it had a radius of 50 millimeters and a height of 70 millimeters, that would fit their new constraints on the can. So whatever you picked, 40, 40, 40, 70 would work. Any of those. All right. All right, good job. So because of our shortened time,